A very good day, students. So here I am discussing about the pi molecular orbital diagram of some systems having alternating double bonds. For an example, I am discussing first the pi molecular orbital diagram for butadiene, that is 1,3-butadiene. So as you can see, the structure of 1,3-butadiene is that having some alternative double bonds, that is CH2 double bond CH, single bond CH, then again double bond CH2. And as that system has some alternating double bond that can participate in conjugation, that you already understand, that resonance. So that pi bond gets shifted over there and this pi bond gets shifted over there and thereby forming an anion. So now due to the presence of this alternating double bond, that C3-C2 bond, although that has a single bond character that do not rotate about its axis, that is this type of rotation is not possible. As you know, a single bond has is looking like some cylinder, that has some cylindrical shape, and the electron densities are just at the round side of this cylinder. Okay, but so that's why this C3 bond, say C3-C2 bond, can rotate. But due to this conjugation, this C3-C2 bond gets some partial double bond character, and that's why it cannot rotate. That is one of the point. And all the carbon atoms here are sp2 hybridized. As you can see this structure, all the carbon atoms are sp2 hybridized. So there is one unhybridized p orbital is present in this each of the carbon atoms, say C4, C3, C2 and C1. So I have drawn this unhybridized p orbital over there. As you can see, this is C4, this is C3, C2 and this is C1. These are the unhybridized p orbital. Now for doing the pi molecular orbital, you have to count how many pi bonds, or say how many double bonds are there. As there are in this system, as there are 2 double bonds, we can calculate there are 4 pi bonds. Okay, each double bond means 2 pi electrons. So there are 4 p orbitals. We can say there are 4 p orbitals. As there are 2 double bonds, we can say there are 4 p orbitals. And from the knowledge of molecular orbital theory, as you know, the total number of molecular orbitals formed is equals to the number of participating atomic orbital. So as there are 4 p orbitals are participating in the formation of this molecule, so obviously these 4 p orbitals of carbon mix by linear combination of atomic orbital and thereby forming 4 molecular orbitals. So before starting the drawing, we have to remember some basic points. Number 1, there are 4 pi molecular orbitals in this system, as you can see. Number 2, out of these 4 pi molecular orbitals, 2, that is half, are bonding, participating in bonding MOs, and half, the rest 2, are anti-bonding MOs, same molecular orbitals. And another formula that you have to remember, the number of node. Now about node is what? Node is the region in space where the probability of finding electron is 0. Okay, and the formula is n-1, where n is the energy level value. Now let's start the drawing. So you have to draw the energy axis first along y-axis, and what I have discussed recently, there are 4 molecular orbitals because they are coming by the combination, say LCAO combination of 4 p orbitals. So these are the 4 molecular orbitals. So first you have to draw 4 straight lines, 4 parallel straight lines like this way, and then you have to draw the p orbitals like that way. From bottom part to upper part, that will be designated by pi 1, pi 2, pi 3, pi 4. You may also designate it by psi 1, psi 2, psi 3, psi 4. That is your choice. And half of these will be bonding, say psi 1, psi 2 or pi 1, pi 2 will be bonding, and the rest 2, say psi 3, psi 4 or pi 3, pi 4 will be anti-bonding. Anti-bondings are designated by star marks, right? Now first I am just starting the pi 1. So for pi 1, the number of node will be 0. What I have discussed recently, that is number of node equals to n-1, where n is the energy level. So for energy level, that is 1. So 1 minus 1, that will give you 0. So how to draw 0 node? So as you can see, these are the hazy surface. So hazy surface, all the 4 carbon atoms p orbital hazy surface are in one side. So all of the carbon hazy surfaces are in one side and they are forming some bonding interactions. So C1, C2, one bonding interaction, C2, C3, another bonding interaction, C3, C4, another bonding interaction. So there are 1, 2, 3. So there are 3 bonding interactions. So as you can see, I have written over there, number of node equals to 0, number of bonding interactions is equals to 3, and number of anti-bonding interaction is equal to 0. So no node is there. So total number of node will be equal to the number of anti-bonding interaction, that you must remember. Second, come to the pi 2 or psi 2. Here we have to draw one node. So as you can see, I have draw a dotted line over the C2 and C3 carbon atom p orbital, where the two opposite lobes are present. So there is one shaded part, and there is just above the lobe, above the p orbital, there is one shaded part, and below the C3 carbon atom there is one shaded part. So there is one anti-bonding interaction. Okay, there is one anti-bonding interaction, and there is one bonding interaction, and there is another bonding interaction. So that's how you have to draw. So first, how to draw? First, shade all the p orbital in one side. All p orbitals should be shaded, and then 2 p orbitals are shaded in one side, and the opposite 2 p orbitals are shaded in another side. So then you can get one node in this portion, that is C2, C3. So here number of bonding interaction is 1 and 2, that is 2 bonding interaction, and anti-bonding interaction is 1, that is equals to the number of node. Now come to psi 3 or pi 3 star. So here you have to draw like this way. There are number of node should be 2. Number of node is 2. So here you have to draw 2 dot lines, 1 dotted line and 2 dotted line. So here one shaded part and there one shaded part. You have to draw the shaded part alternatively. That is, if you draw the shaded part here, that is below of the p orbital, then in the next part you have to draw the shaded part upper of the p orbital. That is for this C3 carbon atom. Sorry, this is C2 carbon atom. So that is one non-bonding interaction, or say one node. Similarly here, that is one shaded part and that is one shaded part. So there is one non-bonding interaction, so that is one node. So there are 2 non-bonding interaction in this psi 3 star or pi 3 star, and only one bonding interaction. And at the last you have to draw the 3 node. 3 nodes are there. So alternatively you have to shade the orbitals like this way. This is the first anti-bonding, and this is the another anti-bonding, and there is another anti-bonding. So there is 1, there is 2, and there is 3. So there are 3 nodes, or you can say there are 3 anti-bonding interaction. So number of bonding interaction will be 0 here, as you can see. So there are 3 dotted lines I have put over there, and there are 3 non-bonding interactions or 3 nodes. Now I have to focus on the HOMO and LUMO. So how many electrons are there? There are 1, 2, 3, 4. There are total 4 electrons in this molecule. So I have draw 4 electrons over here, and just as you fill the electrons in the molecular orbital, here also you have to fill the electrons in the molecular orbitals, in the pi molecular orbital. So in accordance to Hund's rule, like 1, 2, 3, 4, so each box will contain a maximum of 2 electrons. Okay, so here 2 electrons are present. So that will be that means psi 2 will be the HOMO, that is highest occupied molecular orbital. Now that is the ground state. Now if I do the excited state, then one electron from psi 2 will be excited to the psi 3 or pi 3 star. So in that situation, that will be the HOMO. So if one electron will excited from psi 2 to psi 3 star or pi 2 to pi 3 star, then that will be HOMO. That is, one electron will be present in that case, so that will be HOMO. And in that case we can say that is LOMO, that is lowest occupied molecular orbital. That is, psi 1 is the lowest occupied molecular orbital, and psi 2 is the highest occupied molecular orbital.